Hello, I'm Srihari. With me are Raj and Nick, and in this lecture, we're going to talk a little bit about unsupervised learning in LFD. Um, so, a quick overview of unsupervised LFD. Unsupervised learning specifically, our goal is to train an unsupervised learning algorithm to somehow gain an insight on data without ground truth labels. What we mean by this is we want to cluster or associate different features or specific qualities in the data to groupings of our input training set. And we're trying to learn new representations or produce generative models using the data. Meanwhile, in supervised learning, as a parallel, it learns a function to approximate labeled data, and this involves a large amount of expensive human labor, and sometimes labeling can be infeasible. So that's why unsupervised is a popular approach to solving this problem. Some pros of unsupervised learning. There's no need to have labeled data, which means that we don't have to go through that taxing, expensive process of finding ground truths. We can find hidden patterns embedded in the data. We can easily reduce the dimensionality of our training set to find important features in the data. And also, it's quite similar to human intelligence in terms of clustering and forming relationships. Meanwhile, the cons of unsupervised learning include the need for large amounts of data in order to learn. There is no feedback mechanism or loss function, so this is a con of not having that labeled ground truth. And finally, the classes that follow after unsupervised learning will still need to be labeled, and to find the appropriate number of classes and the types of classes is another process. So now we're going to go over paper 1, and Raj is going to take over from here.
So the general overview of the first paper, Efficient Learning for Collaborative Tasks, is that you can essentially learn human types through unsupervised learning, essentially a clustering of sequences based on demonstrations. And using IRL, you can ascertain a reward function for each of those human types and incorporate that into a mixed observability Markov decision process to essentially pick the most appropriate policy aligned with the preferences of a user. In this paper, they conducted testing with a human and a robot doing a collaborative task of finishing a box. So the general overview of the algorithm is that you essentially take a input database of sequences and you cluster them based on the human types. So essentially how a person likes to do the task. And then based on those human types, you can learn a reward function for each of those clusters and input that into a MOMDP setting. And then given sequences of new user data, you can infer a user type based on that and then align the policy from the MOMDP towards that human, and then they can then proceed to do the collaborative task. So the clustering algorithm is essentially a algorithm that first finds the number of clusters k by calculating the dispersion, the within cluster dispersion for a range of values for k, such that adding another cluster doesn't necessarily result in a significant decrease of dispersion. So essentially very similar to k-means, for example. And then once you find the number of clusters k, you can then initialize these transition matrices, theta hat, for each value of k, and also initialize array of z of sequence assignments for each of the trajectories x1 through x of n. And given those trajectories, you can essentially do an expectation maximization process where you assign, in step 4, assign each sequence to its appropriate cluster given the highest log likelihood of it belonging to that cluster. And then the M step, line 5, each cluster's transition matrix is updated by counting the transitions in all those sequences assigned to that specific cluster. And then you do this expectation maximization until your sequence assignments converge into a stable Z matrix. Now, one important aspect of this paper is understanding what a mixed observable Markov decision process is. Given what you probably already know about an MDP, this just essentially builds off of that. So instead of a tuple of X, your state, your actions, your transition matrix, your reward function, and gamma, instead you have a tuple of X, Y, S, AR, TX, TY, R, omega, and O. X is your set of observable variables, essentially what your current task step is. Y is the set of partially observable variables, such as your human type, with S being the set of states in the Markov decision process, A being the set of actions that you can take, T being the transition probability matrix for your task steps, Ty being the transition probability matrix of your human types, R being the reward function, omega being the set of observations the robot receives in the online phase, and then O being the probability function of an observation based off of your state. So, given that introduction to mixed observability Markov decision processes, we can essentially conduct IRL on each of those clusters to learn the human type, a reward function for each of those human types. So in order to do this, first you reduce the MOMDP to a general Markov decision process of just X, AR, TX, R, and Y. And then for each of those clustered human types, IRL is then applied to learn that reward, matching the feature expectations between the policy and the feature expectations of the human type. So equation 5 is essentially the feature expectations of the human type, with phi being the vector of features, gamma being your discount factor, and then being done so for each Z human type. And given that set of reward functions, you can then use SARSOT to compute an approximate optimal policy, taking into account the new human demonstrations in an online phase. And then in the experiments conducted by the paper, there were 3 experimental methods, essentially a manual method in which verbal annotations were used for the data, a method called Auto 1 in which they use reinforcement learning in the MOMDP construction, but in this case, the reward functions were manually hard-coded. And then the third method, which is the method introduced in the paper, Auto 2, using clustering and IRL. And the testing methodology was essentially using 36 human participants. Each person was meant to work collaboratively with a robot to refinish the surface of a box, and the robot's role was to change the position of the box to match the human's preference. And given this test, the 3 hypotheses the paper wanted to test was that 1, manual control will be less anticipatory. 2, the performance of Auto 1 and Auto 2 will be comparable. And in the quantitative sense, they wanted to test in the third hypothesis that teams with auto agents outperform those with manual agents. From a qualitative standpoint, they use a 3-way Friedman test. And you can essentially take a look at the question 2 probabilities, and when p is less than 0.01, it essentially says that that is statistically significant. And in that section, when you compare Auto 2 and Auto 1 relative to the manual method, P is more statistically significant, and question 2 is essentially asking the robot, did the robot anticipate your actions? And you can make the claim that manual control is less anticipatory based on that. And then in response to hypothesis 2, 2 tests were conducted, a toast equivalence test, which essentially just asks human participants to rate the similarities between auto 1 and auto 2, and they were rated similar. And the pairwise Wilcoxon test, signed rank test, where it was agreed that the participants agreed that auto 2 was more responsive than auto 1. In a quantitative sense, the third hypothesis, that the teams with auto agents outperform those with manual agents, does not hold. Essentially, the task completion time doesn't necessarily change between the 3 methods. What does change, though, is the smaller variance in the auto methods, although that essentially would be more applicable for a manufacturing setting, not necessarily a perceived benefit, though. And overall, what this paper did show was that learning human user models through these joint action demonstrations and encoding them in a MOMDP formalism does support effective teaming in these collaborative tasks, but there are still open-ended questions left. And essentially, one of the claims that this paper makes is that the learned policy is robust. Do you think there was enough evidence for this?
I personally don't think there is enough evidence to claim that the learned policy is robust, specifically because there's only one experimental setup, and it didn't thoroughly test the benefit of the paper's proposed method over other methods, and for that reason, I don't think it was exactly robust.
Another claim the paper made was that they claim to have learned human user models and adjusted for these preferences. Is that necessarily true through the actual experiment that they conducted?
The paper didn't really talk about how adjusting for different user preferences was achieved. We don't really know how different the human demonstrators were actually were, or if the robot was just doing something that the human perceived was intelligent. So we don't know for sure that the robot modeled the exact user preferences.
And the third question that we had is assuming full observability of task steps fair?
So maybe in a more manufactured setting, this might be fair. Maybe when the environment is more deterministic, more obvious what's going on. But the paper mentions in the case of maybe if the robot is at home, this might not be as fair of an assumption.
All right, and now let's go into the second paper for the unsupervised learning techniques. All right, so overall, training is a large sunk cost in the domains of commercial aviation and military operations. This is largely due to the high cost of the large vehicles that are used in both of these domains. So it can be a lot better for us if we can simulate the training of these domains. So it's often more relevant to train using simulations for this reason. And obviously you want the simulation to reflect the real world as close as possible. So using machine learning, we can learn how these players act within the simulations, how they develop strategies. We can try and predict how they're going to perform in the simulations, as well as recommend lesson plans to help them learn more effectively. So all of those things are what this paper addresses: learning things about the player and learning how we can recommend lesson plans to better educate them. So the simulation developed to study this is a game called Strike Group Defender, and it's a serious game, not a normal game, and it's for the purposes of training. So in this serious game, there were two types of weapons that the player could use: soft kill and hard kill weapons. The soft kill weapons are things like flares to get in the way of a missile that's targeting the player's ship. Hard kill weapons are other missiles that the player could deploy to intercept. So the way this was conducted was there would be a bracket tournament of 148 players from MIT Lincoln Lab, and then there was a second portion of this study where an additional 76 players were included. And there were a lot of different types of levels. There were several tutorial levels, and then also several different types of performance evaluation levels. So the general outline of this paper is going to go as follows. So first, the paper explored discovering player types, and then discovering player tactics or strategies. Then third, predicting how the player is going to perform. Fourth is if you can predict player disengagement while learning the ropes of the simulation. And finally, the work attempted to predict a good lesson plan for better educating the player. So first, let's go into player types. So this was the state space of the players. The work collected many pre-designed features throughout the gameplay, some of which are shown on the screen right now. The intention was to use these values to learn something about how the players were spending their time within the simulation. So within the player types, the data was shown on the previous slide. And so what the work did was they clustered this data using K-means. So the idea is to try and find a certain number of clusters which would correspond to these so-called player types. So now on the screen is the general algorithm, where K is the number of clusters, and this is a hyperparameter of this method. S would be the set of the clusters, and Xi is an observation, where an observation in this case would be the features that was shown 2 slides ago. That was pre-designed and collected during the simulation. And mu here is the centroid or mean of cluster J. So after this work conducted the K-means unsupervised algorithm, there are 2 metrics that this work employed to analyze what would happen, or to try and find an ideal value for the number of clusters. One is the cumulative distance, and the other is the silhouette. So the first shown is the cumulative distance, and this should look really familiar. It's the term used to calculate intra-cluster distance to the cluster's centroid. This is a measure of the overall tightness of the cluster, where tighter clusters yield smaller cumulative distances. So on the screen shown, the arrow between mu, the centroid, and a given data point xi is shown. The second metric this work used is silhouette, and overall it represents how spread out clusters are from each other. So from this formula, you can see A of I and B of I, where A of I is defined as the distance between a point, x sub I, and its assigned closest centroid, and B of I is the same thing, but between x of I and its assigned second closest centroid. And you can see A of I between the left cluster on the screen, and B of I is the distance between x of I and the right cluster on the screen. All right, so now let's look at some results. So this is what happened when the work ran K-means from clusters K equals 2 all the way up to K equals 10. And so how, from this result, can we choose what the ideal number of clusters is? And remember, the number of clusters corresponds to the number of player types that's present within the data. One of the ways we can use this graph is to look at the cumulative distance. We want that to be minimized as much as possible, because remember that represents how tight a cluster is. But we can't simply minimize this because it would minimize for perpetuity. Another thing we want is for the cluster to not be too sparse. It should contain a decent amount of data points. So for this, we can use elbow method to see about when the cumulative distance is flattening out. And then for our second metric, the silhouette, we want that to be relatively higher, because that means the clusters are more spread out from each other, approximately. So this work found K equals 4, and this is what they went with. And here you can see some results on what the actual player type clustered would be. The purple bar here represents the features after only 20 games were played, and the blue bar is the average after the player finishes participating in all of the games played total. So cluster A seems to represent the highest achieving players with a high number of repeated games and tutorials, for example, as well as a much higher number of games played in general. And it appears as though cluster C was quite low performing. They had a really low average score, and that is pretty well represented in low ratios of some of the other features. So now let's shift a little bit. So previously we were looking at different player types. Now let's try and look at player strategies. So there's a reason why we can't use K-means for player strategies, and that really just boils down to what does it mean to take the mean of a strategy. You don't want specific actions to be averaged here because then that operation is not really defined for a strategy. So here, that's why this work, we can assume went with K-Medoids instead of K-means. So yeah, now also it can be noted that an observation is changing. Instead of being those predefined features for K-means, now it's going to be different actions, aka different weapons deployed throughout the game. And within a game, there can be a different number of actions deployed. So the number of actions can be different between each game. So because of that, you have different sized sets that you're trying to compare the distance to. And that's why we can't exactly use this formula on the screen. So let's look at what this work used to calculate the distance between two sets of actions that occur during the game. They use the Hausdorff distance, which is defined as shown on the screen. So capital H of set A and set B is equal to the max of lowercase h of the first and second set compared to lowercase h of the second set and the first set. And this is because the operation is ordered. So the lowercase h is defined as the max of the first set subtracted from the min of the second set. And for simplicity, let's look at an example where A and B are from the reals, subset of the reals. So we can see that the first set, the maximum is 10, and the second set, the minimum is 2. So subtracting these two values should give you 8. And then for the second part of the Hausdorff distance, you just swap the order of the sets. So you take the maximum of the second set, which will be 3, subtracted from the minimum of the first set, 1, to achieve max between 8 and 2. So this paper uses delta as a function to define the distance between two specific actions that occur. So first of all, A minus B, in the work they use the time difference between the two actions that occurred, as well as the positional difference between the two actions, where an action is a deployment of a weapon, so that's why it has an x and a y coordinate. And then they also weight this difference by theta of A and B, where theta is defined as either 1, 10, or 100, and this is roughly based on the difference in the category of the type of weapon that's deployed. So that's why you want more different types of weapons to be weighted higher, as opposed to weapons that are of the same category. And here you can see all these values of the weighted distance being plugged in as the distance between two sets, and this is really just replacing the distance between the observation and the Medoid with Hausdorff distance. Otherwise, it's the exact same algorithm as K-Medoids. And now we can look at some results for K-Medoids. So this graphic is a lot to take in, I'll admit, but what you can see is 4 Medoid strategies after the clustering. So the center of every strategy is the ship icon, and the different colors on the radial graph represent 5 soft kill weapons that the players can deploy. Distance from the center equates to time since the game began, and the direction corresponds to the relative direction that the actual weapon was fired relative to the orientation of the ship. So the bars and the asterisks at the bottom show statistical significance between the strategies. So between the first and third strategy, first and fourth, and second and fourth show statistical significance. The right-hand clustered strategy, which was the worst performance, seems to deploy weapons with the most randomness or least intent, while the rest seem to fire weapons with more intent, and that can be seen with less random firing of weapons and maybe some more direction.
So now that we've talked a little bit about player types and player strategies, we can now focus on how to determine player performance and also predict when a player is going to disengage. So in situated learning settings, it's absolutely critical to understand when a player or when a learner is going to disengage, and also how well a player is doing, because this is important for providing feedback to the learner. Predicting when the learner is going to disengage will provide for a more effective learning experience for both the teacher and the learner, for the expert and the student. So in order to address this, the paper finds first finds the most informative features for player performance using a select best features algorithm within their predict player performance algorithm. So first, there's a subroutine to select the most important features. It is a greedy polynomial time approximation algorithm that finds the best features by selecting the most informative feature and then dropping potentially the least informative feature. Then the paper uses, or the algorithm uses, leave one out cross-validation, or LOOCV, and lasso regression to find the best shrinkage parameter given the folds. The shrinkage parameter is used to reduce the effect of sampling variation, which can significantly affect the trained model. As Nick was talking about earlier, there's going to be variations in the data provided. These features and the shrinkage parameter are then used to train the neural network in step 4, and the X-train set is then used to predict performance of the model. Now that we've talked a little bit about the algorithm for player performance, we can talk about how to predict when a player might disengage. So the paper uses a deep neural network approach in order to classify whether a player is going to quit after a set number of games. So it's important to note that the number of games played cannot be an indicator here. So different features such as the number of games quit, the scenarios played, the replays may be used. And also, once again, the paper uses LOOCV in order to maximize the quality of the network. And as mentioned before, this is key for assisting a teacher to guide the learner. The disengagement is able to be predicted after 1, 2 to 5, 6 to 15, and 16 to 30 games using bins of positive training examples. So in bin 1, we have 30 examples of players disengaging after 1 game. In bin 2 to 5, or in bin 2, we have positive examples of players disengaging after 2 to 5 games. In bin 3, we have positive examples of players disengaging after 6 to 15 games, and finally for bin 4, 16 to 30 games. And it's important to note that the predictions got significantly worse with increasing numbers of games played. As you can see, the area under the curve value drops from 0.991, which is almost 100% true positive rate, to 0.83 in the bin 4 case. Now to talk a little bit about the results of player performance and player disengagement. I already talked a little bit about the AUC values. For player performance specifically, we have an AUC value of 0.71 with 63% true positive rate and a 33% false positive rate, which means that optimal features were learned and a model was trained to relative success and it was able to predict performance. It's also important to note that the players that were predicted to perform highly actually quit more games, and this is likely because the players that were predicted to perform highly were very confident in their own ability to play SGD, and as a result quit the games because they felt there was no reason to continue, because they'd already learned how to play. However, there is no consideration in this entire algorithm of the order in which the levels are played in SGD specifically. So we can talk a little bit more about that in a future slide where we introduce lesson plans. For player disengagement, the model, the deep neural network, is able to predict which players will disengage and after a certain amount of games, right? And it can predict who will disengage after a very few games almost perfectly. As mentioned earlier or in the previous slide, we saw that after one game, the model is almost 100% accurate in determining which players are going to disengage. But as we decrease, or as we increase the number of games played, it becomes consistently harder to predict when the player is going to disengage. And this is likely either because of the amount of negative examples decreasing, which means that there are fewer examples to train the model on, and it also might be easier to predict players that drop earlier, given their feature set. Moving on, the culmination of all this work is a generation of an effective lesson plan using expert data. We want to show that, or somehow classify our top and bottom performers and determine the optimal series of games played in SGD that will allow a player to become optimal or become a top performer. We can define an HMM, which is a 5-tuple omega consisting of x, t, pi, sigma, and e, where x is the hidden states, the set of hidden states, t is the transition probabilities between the set of hidden states, pi is a prior, or rather the initial belief state, sigma is the set of emissions or potential emissions, and E is the emission probabilities. The goals of this model are to be able to predict player performance based on a sequence of levels played, or generate a lesson plan to improve player skill given a belief state and a set of previous emissions. The Baum-Welsh algorithm is used here to find transition and emission probabilities given optimal or suboptimal state series, as we'll see in the next slide. So the HMM is used to predict whether a player is in the top or bottom 50%, or it can be used to figure out an optimal lesson plan for the top performers or the bottom performers based on their existing performance. The AOC for the HMM-based approach is 0.79 versus 0.71 for predict player performance. This might show that this might indicate that the HMM outperforms predict player performance, but predict player performance uses other features, specifically games played and games quit, etc., rather than the actual sequence of states or the sequence of games played in order to make a prediction on either the performance of the player or the sequence of tutorials or future sequence of tutorials. So one might ask why simply not looking at a frequency of games played is not enough here in order to determine a lesson plan. And this is because the paper performs a chi-square analysis of whether frequency is indicative of performance. So for example, we see the basics tutorial has a frequency of approximately 0.05. The Moth missile tutorial has a frequency of a little higher. And some of these values are different between the best players and the worst players, but most of them are relatively similar. And as a result, this is more of a visual indication, but after a statistical analysis, the null hypothesis is not rejected, which means that the frequency of games played is not a good indicator of player performance. And thus, in conclusion, the order in which the games are played is a significant indicator, at least according to the paper. And this is kind of supported by the AUC of the HMM-based approach being lower than the AUC of the original predict player performance approach. So now we can talk a little bit about generating lesson plans. Suppose we have two, so we create, the paper creates two HMMs, one modeling the top 50% of performers and one modeling the bottom 50% of performers. Plans can be prescribed a priori, which means that there can exist a lesson plan before the player has played the game at all. which can indicate an optimal set of games to play in order to become or in order for the player to be one of the top 50% of players. So what this model is really saying is that in order to be classified as an underperformer, the sequence of training levels is on the left can be used as used for the game. However, for optimal players, the sequence on the right may be chosen in order to be in the top 50%. And as the player plays more levels, this lesson plan can actually be tailored for the player, and this is because HMMs are generative, and new lesson plans can be created on the fly in order to train the player. The HMMs generated are cross-validated with leave one out cross-validation as used in previous methods, and a single HMM in this method is kept out of the 250 generated in order to compare to the original HMM created in order to do the cross-validation. And the result, as you can see on the right visually, there is a much different lesson plan for the bottom 50% of players and the top 50% of players. The top 50% has much more variance or variations in the games played in order to become a top performer. Whereas on the left, as you can see, there are only 2 tutorials that are actually played, which leads the players into the bottom 50% of performers. So now that we've gone a little bit over the supervised approaches used in paper 2, we can conclude by going over once again the unsupervised approaches, which cluster the player types and the player tactics. The paper uses K-means and K-Medoids in order to accomplish this, and different player strategies can be extracted in order to gain insight into what actions the players take. However, supervised learning can be used in order to predict player performance, predict disengagement, and also create individual lesson plans, which can be informative for a teacher in a supervised learning setting, or rather a situated learning setting, in order to guide the player or guide the learner. Moving on to questions. First of all, is the proposed method mimicry, emulation, imitation, or none of these? So I'd personally make the argument that this is mimicry because there's no real reasoning about the goal. We're simply taking a cluster of top performing players in the game and training an HMM on that without actually thinking, or the model is not actually considering what the true goal of the LFD is. It's simply trying to find a set of lesson plans for the top 50% of performers instead of actually thinking about whether the resulting player would be in the top 50% or in the bottom 50%.
So yeah, counter to that, I genuinely think this could be in the realm of emulation, in the sense that the intention behind this HMM is essentially to help the player with this lesson plan to get better. So essentially, with that, you do have a goal in mind. So, to me, this feels like it's a gray area where I do think it can fall into emulation, although a strong argument would have to be made that an HMM can actually reason about goals.
Oh wait, yeah, I think there's an actual argument to be made here for either mimicry or emulation. The second question is, the paper indicates that the frequency of games played is not statistically significant, or is not a statistically significant indicator of performance. But does this mean that the order must be a statistically significant indicator of performance?
I argue that it might not be. For example, maybe you can factor in player disengagement. So if you start with a really hard tutorial and then move on to really easy tutorials, maybe you don't learn that much from the harder tutorials, and it could also make you disengaged. But perhaps someone could be disengaged or not disengaged and then go back to the harder levels afterwards and still become a great player of this simulation.
And judging that the human types were extracted in section 5 and 6, could multiple HMMs be trained on individual human types to determine the optimal lesson plan in order to get to that quality of player?
I actually think this would make for really interesting future work, essentially creating specific, not just generalizing lesson plans based on like a top 50% users or top bottom 50%, but essentially making personalized lesson plans based on just single human type data would be an interesting thing to look at.